Friends, this is your last video that you need to listen to or watch of me this week. Congratulations. Okay, it'll be short. Last thing we're chatting about in this section, and it's linked with this section because we're talking about planets, we're talking about the force due to gravity in this circular motion unit. We need to chat about geophysics. So that's gravity near the surface of the Earth. And when we focus on gravity close to Earth's surface, we can use the law of universal gravitation to calculate slight differences in gravity based on location and based on elevation. So we've been just saying that G equals 10 meters per second squared. That works for our calculations. That gives us pretty good results, pretty decent, accurate results. Officially, gravity is closer to 9.8 meters per second squared. But even this value can vary slightly depending on where you are on the Earth, depending on how high above sea level you are. So whether you're on the top of Mount Everest, whether you're by the Dead Sea, your local gravity is going to change a little bit. These differences are useful in mineral and oil exploration. Different densities will give you different local gravities, so that's kind of cool. You have another little video attached which explains kind of how satellites track water levels on the Earth based on this idea with geophysics here. So the equation that we're going to use to calculate local gravity is your law of universal gravitation. But instead of just F on the one side, you're going to use mg. So this is mass of your object, right? That's just m. And then g, that's going to represent your local gravity. We've been using 10, or more accurately, it's 9.8. But now we're going to actually calculate for g and figure out what is your local gravity. So once again, this is the force due to gravity at Earth's surface. And I'm going to set that equal to our universal gravitation law. So G, mass of the object, mass of the Earth, right? Because those are my two objects that I'm playing around with here, over R squared. Because I have the mass of the object on both sides, that's going to drop out. I don't really care what the mass of that object is. So to solve for, why did that happen? Okay, let's try this again. So you have M times G. You're going to cancel out M. You're going to get G equals that gravitational constant times mass of the Earth over R squared. All right. So this lowercase g is going to represent gravity at the surface, and it's going to vary based on this R value, based on how far away from the center of the Earth you are. So a quick example with this. Estimate the effective value of gravity G at the top of Mount Everest. Mount Everest is 8,850 meters above sea level. So your R value here will be 8850 meters, but plus Earth's radius, which is a number that I will just give to you. I would not expect you to have this one memorized. Earth's radius is 6,380,000 meters. When you add these together, we'll get 6.389 times 10 to the 6 meters, okay? That's the distance between this object, whatever the object is at the top of Mount Everest, and the center of the Earth. And then the mass of the Earth, that's another number that I will provide for you. I wouldn't need you to know this, 5.98 times 10 to the 24th kilograms. And then G is our lovely 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. So when we plug this in, so this is going to be G top of Everest, you're going to get 6.67 times 10 to the negative 11. I'm going to drop units. Units work out. Over, or times 5.98 divided by 6.389 times 10 to the 6. Make sure you square that. Square. Okay, when you plug these into your calculator, you're going to get 9.77 meters per second squared. So this is definitely lower than what we usually accept for gravity. And slight differences like this can actually mean a lot, depending on the types of calculations that you're trying to do. last thing we're going to chat about in this section, we're going to start talking about satellites. We're going to talk a lot more about satellites next week and after Thanksgiving. So satellites rely on Earth's gravitational force to keep them in orbit. So Earth's gravitational force to stay in orbit. Using rockets, satellites are put into orbit, so you need something to kind of get them up there, and then Earth's gravitational force keeps them in orbit. But they also need to keep on accelerating. If there was nothing kind of forcing the rocket to have some kind of velocity, then Earth's gravity would just pull them back to Earth and they would crash. So the way satellites stay up is they're held in orbit by gravity, by gravitational force, but then they also need a very high speed or high velocity. Okay, so up here, very high speed. So if you think about this, if you visualize this, here's the Earth. This would be our orbit. If Earth's gravity wasn't playing a role, it would just keep going on. The satellite would go forever and ever. So this is without gravity. With gravity, you're going to follow this beautiful circular path. Okay, so what keeps satellites up? It's the satellite's high speed. If the speed is too low, the satellite will fall towards the Earth. If the speed is too high, the satellite will fly off into space. So you need both gravitational force and very high velocity to keep satellite up. So here's an example that we could do with this. A geosynchronous satellite, it's just a special type of satellite, is one that stays above the same location on Earth, meaning the satellite rotates exactly with the Earth, and t is going to equal 1 day. Determine the satellite's height and speed. Okay, so I have t. I know that's 1 day. We would need to convert that to seconds. So times 24 hours in 1 day times 3,600 seconds in 1 hour. You're going to end up with 86,400 seconds. We're going to need to know the mass of the Earth, right? Because that's kind of our other object at play here. That's 5.98 times 10 to the 24th kilograms. We might need to know our gravitational constant, 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. And they're also telling us that Earth's radius is 6,380 kilometers, or 6.38 times 10 to the 6th meters. So remember, convert from kilometers to meters. That's where this 10 to the 6th is coming from. So I have the Earth. I have Earth's radius over here. And then I have my satellite orbiting. And it's at some kind of height. That's what they're asking us to figure out. It's at some kind of height above the Earth. I'm going to call that h. And it's going at some kind of velocity, and that combination of Earth's gravitational force and its velocity are keeping this thing in orbit. So here's how we're going to tackle this one. We're going to start out going all the way back to F equals ma, because remember, even when we're doing circular motion, everything goes back to F equals ma. The force at play here would be gravitational force. So I'm going to use Newton's universal law of gravitation. G, mass of the satellite, mass of the Earth, those are my two objects, over the distance between them squared, equals m, so that's the mass of the satellite. And then a, okay, it's circular motion, so it would be centripetal acceleration, so it would be v squared over r. Because I have the mass of the satellite on both sides of the equation, I'm going to cancel that out. And I also have r in the denominator on both sides, so I'm going to cancel out this r with one of the r's over here. So what I have now is g, mass of the Earth, over r, distance between the center of the Earth and the satellite, equals v squared. Well, v, we know, is also 2 pi r over t. Okay, I like that. I don't totally know what this r value is. Yes, I know the radius of the Earth, but r in this case really represents radius of the Earth plus the height of the satellite above the Earth, right? Because r is the distance between the satellite and the center of the Earth. So I don't totally know what r is yet. I'm going to need to actually solve for r to figure out what my height is. I do know what t is, so that's cool. But I like that I could replace v with an expression with r and t in it. That's going to help me. So I'm going to take this expression, I'm going to plug it in here for v. So I have g equals mass of the earth, not equals, g times mass of the earth over r equals 2 pi r over t, that whole quantity squared. That's going to be 4 pi squared r squared over t squared. Okay, here's what we're going to do. I know that g constant. I know the mass of the earth. I'm trying to solve for r. I know t. I want to get r by itself on one side of this equation. I have an r over here. I have an r squared over here. I need to somehow combine those up. I'm going to do that by moving over the 4, the pi term, the t term, and by moving over the r. So I'm going to multiply both sides by r. So now I have g me equals 4 pi squared. R squared times r would be r cubed over t squared. And then I'm going to multiply everything by t squared. I'm going to divide everything by 4 pi squared. Okay, so we are left with r cubed equals g, mass of the earth, period squared, over 4 pi squared. All I've done here is I took my initial equation, I substituted in a better expression for v, an expression with something that I wanted to find and something that I already knew, r and t, and I'm just rearranging right now. I'm doing a bunch of rearranging. I'm trying to solve for r. That is my goal here. So then to get r, you need to take the cube root of both sides. You would plug in a bunch of stuff. Okay. So over here then, r is going, well, actually, let me just use this over here. Take the cube root of both sides, right? Okay. So I'm going to get r equals the cube root of g, 6.67 times 10 to the negative 11th, times the mass of the earth, times t squared, all over 4 pi squared. And you're going to take the cube root of that, and the answer you're going to get is r equals 4.23 times 10 to the 7th meters. So the cool part is we're not done yet. So that's r. Remember, I want to try to find h. To find h, I need to take that r value we just found and subtract the radius of the earth from it. So 4.23 times 10 to the 7th meters minus the radius of the earth, which is 6.38 times 10 to the 6 meters. Plug that into your calculator. You're going to get h equals 3.6 times 10 to the 7th meters, or about 36,000 kilometers above the earth. So that's the satellite's height. If you wanted to find the satellite's speed, you could either just plug back into this equation, the v equals 2 pi r over t. You could totally do that. You know what its r value is at this point, that 4.23, so you could just plug in there. That would work. Or you could use this expression over here to solve it for v. V is going to equal g, mass of the earth, divided by r. This is something that you'll see a lot, especially when you're dealing with satellite problems. This is a good satellite equation to keep in mind. So you can use either one of these to solve for v. If you plug into either of those, your v is going to be 3,070 meters per second. All right, you're done. Congratulations. Have a lovely rest of your week. Have a good weekend.